The Sun, our life-giving star, has been shining in the center of the solar system for billions of years. To understand its age is to peer deep into the heart of astrophysics, following clues woven into the cosmos itself. The Sun's story began in a swirling cloud of gas and dust in the Milky Way galaxy about 4.6 billion years ago. Scientists have pieced this together using a combination of methods: dating meteorites, examining the oldest rocks on Earth and the Moon, and modeling stellar evolution. Meteorites, remnants from the dawn of the solar system, act as natural time capsules. Isotopic dating of these ancient rocks reveals that they formed about 4.56 billion years ago, just as the Sun ignited. The oldest Earth minerals, zircons found in Western Australia, date back to around 4.4 billion years, supporting this timeline. By comparing the Sun's luminosity, mass, and chemical makeup to theoretical models of star evolution, astronomers confirm that the Sun is a middle-aged star, about halfway through its main sequence lifetime. In cosmic terms, the Sun's galactic age situates it as an anchor point in the history of our galaxy, one of hundreds of billions of stars weaving the tapestry of the Milky Way. But the Sun's age is not just a number. It's a key to understanding our place in the universe. Over these billions of years, the Sun has orbited the galactic center more than 20 times, moving through spiral arms, encountering cosmic phenomena, and shaping the conditions for life on Earth. Its stable output has allowed the emergence and evolution of life, while its eventual transformation into a red giant will mark the end of this era. The galactic age of the Sun is a bridge between the primordial chaos of star formation and the unfolding drama of planetary systems. Yet the Sun's story is only one chapter in a much larger cosmic narrative, one that includes mysteries like dark matter. For decades, astronomers have grappled with an unexpected problem. When they observe galaxies, including our own, they find that stars orbit at speeds that cannot be explained by the visible matter alone. According to Newtonian physics, stars further from the galactic center should orbit more slowly because the gravity holding them in place weakens with distance. But instead, their speed remains nearly constant, defying expectations. This puzzling observation led to the concept of dark matter, a mysterious, invisible substance that does not emit or absorb light, yet exerts a gravitational pull. Evidence for dark matter first emerged in the 1930s, when Swiss astronomer Fritz Zwicky studied the Coma cluster of galaxies. He found that galaxies were moving much faster than could be accounted for by the mass of stars and gas alone, suggesting the presence of unseen dark matter. In the 1970s, Vera Rubin's detailed studies of spiral galaxies confirmed that stars in the outer regions rotated at unexpected speeds, providing compelling evidence that something invisible was holding these galaxies together. The search for dark matter has evolved into one of the most profound quests in modern science. Astronomers have mapped its influence on cosmic scales, observing how it shapes the formation of galaxies and clusters, bends light from distant objects through gravitational lensing, and leaves an imprint on the cosmic microwave background, the faint afterglow of the Big Bang. Despite its pervasive presence, dark matter has never been directly detected. It does not interact with electromagnetic forces, making it invisible to telescopes. Instead, scientists infer its existence from its gravitational effects. Several theories attempt to explain what dark matter might be. The leading candidates are weakly interacting massive particles, WIMPs, hypothetical particles that rarely interact with normal matter. Another possibility is actions, extremely light particles predicted by certain extensions of the standard model of particle physics. Underground laboratories around the world, shielded from cosmic rays, are searching for faint signals of dark matter particles colliding with atomic nuclei. Space-based experiments probe the cosmos for indirect signs, such as gamma rays produced when dark matter particles annihilate one another. Dark matter is not just a cosmic curiosity. It is fundamental to understanding the structure and evolution of the universe. It outweighs ordinary matter by a factor of 5, sculpting the cosmic web of galaxies and influencing the fate of the universe itself. Without dark matter, galaxies would fly apart, stars would not cluster into the majestic shapes we observe, and the universe as we know it would be profoundly different. While scientists search for answers in the depths of space, another frontier beckons: Mars, the red planet. For centuries, Mars has captured the imagination of humanity. Its rusty surface, polar ice caps, and mysterious canyons inspire dreams of exploration and discovery. In recent decades, robotic missions have landed on its surface, probing its geology, climate, and potential for life. But as we prepare to send humans to Mars, a new challenge emerges: the risk of contamination. Contamination of Mars can occur in two directions: forward contamination, where Earth organisms hitch a ride on spacecraft and colonize the Martian environment, and backward contamination, where Mars material brought back to Earth could pose risks to our biosphere. The stakes are high, especially in the search for life. If Earth microbes were to survive and thrive on Mars, they could obscure or destroy native Martian life, making it impossible to distinguish between indigenous organisms and accidental stowaways. To prevent this, planetary protection protocols have been developed, overseen by organizations like NASA and the Committee on Space Research, COSPAR. Spacecraft destined for Mars are meticulously cleaned and sterilized, using techniques like heat, chemical agents, and radiation to eliminate potential contaminants. The level of sterilization depends on the mission's goals. Probes that will touch the surface or drill into subsurface environments require the highest level of scrutiny. Despite these precautions, the risk remains. Microbes are extraordinarily resilient, capable of surviving extreme conditions, from the vacuum of space to intense radiation and temperature extremes. Experiments have shown that certain bacteria and spores can endure the journey through space and might even survive on the Martian surface, protected by dust or within spacecraft crevices. As human missions approach, the complexity increases. Astronauts themselves carry trillions of microbes, and human habitats will inevitably shed biological material. The implications of contamination extend beyond the search for life. Mars has environments that could theoretically support life, such as subsurface ice, seasonal methane emissions, and ancient riverbeds. If Earth life takes root, it could alter these environments, create false positives in life detection experiments, and compromise the scientific integrity of Mars exploration. To safeguard the search for life, some experts advocate for zones of biological interest, areas where access is restricted until more is understood. Backward contamination, while less likely, poses its own risks. Samples returned from Mars must be handled with utmost care, quarantined in secure facilities designed to prevent any escape of potentially hazardous material. Protocols are in place to analyze and contain Martian samples, ensuring that any unknown organisms or chemicals are identified before they can interact with Earth's biosphere. The ethical dimensions of planetary protection are profound. Mars is a unique world, shaped by billions of years of cosmic history. If life exists, or once existed, on Mars, it could answer fundamental questions about the origins of life, its prevalence in the universe, and the potential for humanity to thrive beyond Earth. Preserving the pristine character of Mars is not just a scientific necessity, it is a moral responsibility. Looking ahead, the intersection of the Sun's galactic journey, the enigma of dark matter, and the quest to explore Mars reflects the boundless curiosity of humanity. Our Sun, born from the remnants of ancient stars, orbits through a galaxy shaped by invisible forces. The evidence for dark matter reminds us that the universe is full of mysteries waiting to be unraveled. Mars, with its promise and peril, calls us to explore responsibly, balancing discovery with stewardship. In the coming decades, new technologies and missions will deepen our understanding of these cosmic themes. Advanced telescopes will probe the nature of dark matter, mapping its distribution across the universe. Robotic explorers and human missions will unlock the secrets of Mars, searching for signs of life and safeguarding its environments. The Sun will continue its steady journey, illuminating our path through the galaxy. These stories are interconnected, each revealing a facet of the grand cosmic puzzle. The age of the sun connects us to the history of our galaxy, a timeline marked by star formation, planetary evolution, and the emergence of life. Dark matter shapes the architecture of the cosmos, an invisible scaffold holding galaxies together. Mars represents the frontier of exploration, a reminder that our actions carry consequences beyond our planet. As we gaze up at the stars, ponder the mysteries of dark matter, and dream of footsteps on Mars, we are participating in a journey that began billions of years ago. The quest for knowledge drives us forward, inspiring generations to look beyond the horizon, to seek answers in the darkness, and to protect the worlds we explore. In the vast expanse of the universe, our story is just beginning, a story shaped by the light of the sun, the shadow of dark matter, and the red dust of Mars.